So we will start. Hello to everybody. So we will start now the timing session. So good morning, good evening, good afternoon, and this is the starting for the timing session and synchronization and real-time application session. Thank you for the handover, Dorico and Reinhard. I'm Oscar Matilla from the Alba Synchrotron, and I have the pleasure of co-chairing this session with Javier Serrano from CERN. And Javier has kindly covered the sudden emptiness left by Nicolas Jambier from DSRF. Nicolas was deeply involved in setting the track program during the ISAC and program committee meetings, but sadly he passed away 3 months ago. So we would like Javier and I to honor his memory with a few words before starting the session. Nicolas was a young man, starting in his 50s, and leaves behind him wife and 4 children. We had the privilege of working with him for many years, and he was a person you could always trust in. He had great values, and he always fostered collaboration and exchange of ideas. So after the first impression of his serious demeanor always was changed after just few words to the reality. He was very close and an honest person, a person you could always share jokes and enjoy a beer with. So Nicolas leaves a big hole in our community and in our hearts.
So hello, I'm Javier Serrano from CERN, and I would like to join Oscar in this tribute to Nicolas. He was first and foremost a great person to spend time with, personally and professionally. My thoughts are with his family and his close friends at work and elsewhere as they struggle to deal with his absence. Nicolas loved timing, so let's honor his memory with an interesting session doing what he enjoyed so much, discussing and sharing knowledge and experience.
So just as a general reminder about the general reminder of all the conference, the talk will be of 12 minutes. We will do the warning after the 10 minutes, just for the speaker to know that there are only 2 minutes left, just for having time for the questions. And you can put your question in the QA, in the WUBA, or just raise your hand and we can give you the floor to raise the question. So our first speaker is Dimitris Lampridis from CERN. And after 10 years in the aerospace sector, Dimitris joined CERN in 2016 and now leads OASIS projects, a huge distributed oscilloscope in which triggering plays an essential role. Today, he will speak about the organization of this triggering system using White Rabbit. So Dimitris, please, the floor is yours.
Thank you very much, Oscar. Can you hear me well? Is my sound okay?
Yeah, fine, perfect.
All right, good. So, hello everyone, thanks for coming. Today I will be talking about the renovation of the trigger distribution of the OASIS system at CERN. This is a quick outline of the presentation. I will first introduce you to some background that is necessary to understand what follows next, which is basically the architecture of the system that we have developed. I will then follow up with the introduction to our test setup and some first results that we have out of this setup. And I will close with some conclusions and most important, the outlook on how we are planning to continue. So first things first, I already mentioned it in the title, OASIS. OASIS is the Open Analog Signal Information System. It has been running at CERN for approximately 20 years now, I think. It is essentially a distributed oscilloscope. So I hope you're familiar with the concept of the oscilloscope as an instrument. What OASIS does is that it allows the operators of the accelerators at CERN to be able to monitor and correlate signals that are found all around the accelerator complex. So all these signals are displayed in one common screen, as you see on the left, looking very much like a normal oscilloscope. So that's, in a nutshell, what OASIS is. And then I also mentioned White Rabbit. White Rabbit has been presented on several occasions in ICALEPCS, in the timing track usually. And for those that don't know, it is an Ethernet-based network, so it can do whatever an Ethernet network does. But then on top of that, it provides 2 very important features. One is the fact that every node connected to the White Rabbit network, it has the same notion of time within less than a nanosecond. The second part is that the network is deterministic, meaning that even though we do not know exactly when a message will arrive at a given destination, we do know what is the upper bound limit to that delay. So armed with these 2 things, we can do some very, very interesting applications. Then OASIS over White Rabbit, trigger distribution of OASIS. This is now an ongoing project that we do to renovate the way we distribute triggers in OASIS. And we base this on another project called the White Rabbit Trigger Distribution, WRTD in short. This has been presented 2 years ago in ICALEPCS. And the reason we are doing this renovation is twofold. On one side, we want to replace some obsolete hardware. And then we also want to improve our performance and the scalability of the system. As I said, WRTD is presented, but I would like to do a quick recap. So in a nutshell, the idea is that with WRTD, we can have a trigger pulse at a source, which is then replicated in many destinations with a fixed delay. In this example, is 300 microseconds. The fact that it is replicated at exactly the same delay everywhere is because of the fact that White Rabbit gives us the sub-nanosecond accuracy, the other synchronization. Then the other part, of course, is to be able to guarantee that the message will have arrived in these 300 nanoseconds. And this is where the deterministic latency of the network comes into play. So as long as this fixed delay that we choose is greater than the worst case latency of the network, we are guaranteed that our message will have arrived everywhere before that time expires. So once that time expires, everyone fires together and we have the copy of our trigger pulse. Of course, it still applies that this trigger is 300 microseconds late with respect to the source. So for Oasis, what we do is that we actually, during this time, we have our digitizers acquiring data. And when the trigger arrives, we simply stop and we rewind our data back by, in this example, 300 microseconds and find the data at the point of the trigger. So this is more or less WRTD. And then if we move to the system architecture, first I need to explain how trigger distribution happens today in Oasis without White Rabbit. So in the diagram that you see, the yellow part is the timing system of CERN. The timing system in the context of Oasis is basically the source of our triggers. Most of our triggers are related to some event of something that is happening in the accelerators. Then we generate all the pulse triggers that we would like to use from the timing system, and we put all these things together into our trigger multiplexer, the green part in the middle. At the trigger multiplexer, we have all our inputs, and we also have the ability to resynchronize these triggers to some external clock. Typically, this would be, let's say, in a circular accelerator, the revolution frequency of the accelerator. So we can align ourselves to the third, fourth, fifth turn of the accelerator, something like that. Once any realignment happens, then we produce at the output the correct trigger. The important thing in this diagram is that then each output of the multiplexer goes with a dedicated cable to a card that acquires data for us at the other end, the purple side. And the thing is that in the middle, the part with the timing receivers and the multiplexer is located in one central place at CERN, where the triggers are generated and where these external clocks are available. But on the other hand, the devices that acquire the data, for reasons of maintaining signal integrity, they are normally placed close to the signal source. And this could be anywhere in the CERN accelerator complex. So in fact, some of these cables are very, very, very long, and they have to be pulled for each card individually. And if we want to introduce a new card, we have to pull a new cable all the way from the central place to wherever the signal needs to be. So moving on to the way we change this into a White Rabbit solution, this is what it looks like. In effect, we are keeping the timing system intact. We are keeping our trigger multiplexer intact, and we replace the long cables with a White Rabbit network. So instead of having a dedicated cable per multiplexer output for each one of our acquisition systems, we connect everything to a single fiber-based White Rabbit network. The idea then is that when a pulse is produced at the output of the multiplexer, our trigger, we immediately timestamp it, send it over the White Rabbit network. As I described before, this will arrive with a fixed latency at the destination. And once it arrives, we rewind that data back to the point of the original timestamp, and we deliver this to the user. For testing, we have set this fixed latency to 400 microseconds, which is almost 4 times the worst case latency of the White Rabbit network for Oasis. Then, when there is a new connection request, say that there is a user who wants to connect signal X to trigger Y, what the Oasis server will do is that it will first check if this trigger is already generated for another card. And if it is, it will simply go to the new listening device and it will say that it should listen for the same message. Otherwise, it first reserves a new channel from the multiplexer, configures the TDC to generate a new message, and then configures also the other side. Moving on into the future phases of this project, we would also like at some point to get rid of the multiplexer, because this is actually our obsolete hardware, and digitize, timestamp directly all of our triggers with TDCs inject them in the White Rabbit network. However, for this to happen, we also have to provide the flexibility that was previously provided by the multiplexer, allowing us to resynchronize to external clocks. And for this, we need new hardware developments that will be attached to the White Rabbit network and will provide this feature for us. Moving even further into the future, there is a plan to replace the timing system itself with a White Rabbit-based solution. At that point, the timing events themselves will be White Rabbit messages. So we do not need the TDCs, we do not need to timestamp anything. We simply work on a fiber-based White Rabbit network where everything is just timestamps and events exchanged between the timing system and our acquisition system. Then moving on to the test setup, what we tried in the lab to begin with is very simple. We have here on the left a trigger signal, a pulse, and then we have a copy of that pulse that is delayed by 400 microseconds. We then inject these two triggers into our multiplexer, and at the same time, we provide them as analog inputs to two scopes, scope 1 and scope 2. However, the trigger path is very different between the two scopes. Scope 2 is triggered like in the legacy way with a direct cable, while scope 1 goes through a 10-kilometer fiber inside the White Rabbit network. And so if I show you some preliminary results, this is what it looks like. This is the OASIS graphical user interface. We have two virtual scopes. On the top one, channel 2 is on the yellow line. We have channel 1 from scope 1. So this is our trigger. And then we have the same signal on the other scope, which is triggered with the legacy way. And what we see is that the two triggers here happen exactly at the same time, perfectly aligned. And then we also have the 400 microsecond delayed version on the bottom scope. I do this here in such a, let's say, time base so that you're able to see the two pulses together. But in fact, if we zoom in, this is the image from the first scope. So I remind you again, the yellow line is triggered over White Rabbit. The purple line is triggered with a coaxial cable. And the two systems are identical. They trigger at exactly the same time. They return exactly the same data. So that's it. In conclusion, OASIS is currently migrating the trigger distribution to a White Rabbit-based solution. We are doing this in 3 phases, and we are currently in the first phase. We expect that the first operational deployments of the first phase will be done before the end of this year, but then the full deployment, which is quite a massive operation, will happen in the next 2 years. After that, we'll look into phases 2 and 3, which have currently an estimated time of approximately 5 years starting in 2024. And with that, I would like to thank you very much for your attention.
Thank you, Dimitris, for your presentation. So time for questions. Let me, here in the QA, you can raise your hand or you can put it in Google. I will start before, maybe this one. Yeah, we have one question from that in the QA panel. What is the maximum sampling rate of digitizers?
Well, OASIS creates, let's say, an abstraction layer on top of the hardware of the digitizer. So we use many, many types of digitizers. The one you saw in the example is a 100 megasample digitizer. The fastest ones that we use in OASIS currently are 8 gigasamples per second. And the slowest is 200 kilosamples.
Okay. I have personally one question. Sorry, Javier.
There is a raised hand by Hiroshi Gaji. Maybe he can take the mic or write it down.
Hiroshi, you can talk now.
Yes.
If you want.
Thank you. I have a question about the fixed delay of your setup. You apply the 400 microsecond fixed delay for the I think this is guaranteed to transfer the White Rabbit protocol. And my question is, how much you can shorten that delay? And what is the limit of the this delay? What limit?
So it all depends on the topology of your network. So every time you cross, because this is an Ethernet network, it is based on switches. Every time you cross a White Rabbit switch, the worst case latency introduced by the switch itself is 10 microseconds. So then you have to count for your path the number of switches that you are crossing. Then you have the delay of the fiber itself, that is 1 microsecond per kilometer. And then we also have the delay introduced by the TDC device here, because from the time that it receives the pulse at the input until the message with the timestamp is injected on the network, it takes time, and this is approximately 15 microseconds. And then we also have the inverse of that happening at the destination, from the time the message is received until you are ready basically to produce a pulse. And this is in the order of 40 microseconds. So let's say for a small network, I think it would be in the order maybe of 80 microseconds. I don't see it going below that.
I think
In our
maybe
case,
maybe it's a simple. If we configure as a simple network, it become 80 microseconds. You say.
Yeah.
You mean? Yeah. In case of SUN, it's not possible. Maybe.
No, we have many switches. It's a big network with something like 30 switches. So of course we do not cross all of them all the time, but we have calculated something like 150 microseconds. And for the testing, we just tripled that and we went to 400.
Mm-hmm. Oh, okay. Thank you very much.
Thank you. So any more question? Yeah, here Jose Avila has a question. The digitizers are always acquiring, or do you have a strategy of pre-triggering and triggering?
No, actually, they are not always acquiring. So imagine that a user at the destination asks for something like 500 microseconds worth of data with 50% pre-triggering, post-triggering. We basically, behind the back of the user, we'll ask more pre-triggering to be able to cover for the worst case delay of the network. And when the trigger arrives late, we recenter the acquisition window around the area that the user is interested, discard the rest, and then we return what the user is asking. So no, we do not trigger all the time. We actually trigger when the pulse arrives.
Thank you. I have one personal question about your last figure, about when you measure that the two pulses are arriving at the same time. It was clear that the delay was working. My question is, I'm sure you have measured the RMS jitter, that I guess it will be added the jitter of the White Rabbit with the trigger jitter of the data acquisition system. I'm just curious about this figure. I don't know if you remember that.
No, I haven't mentioned it yet. I haven't measured it yet. It's a very fresh result. So yeah, we are in the process of evaluating what we have. But yes, it's, as you say, this is what we expect.
Okay, thank you. Thank you very much. I don't know if we have time for one final question.
Just a quick correction. I think it was mentioned 1 microsecond per kilometer of fiber. I think he meant 5. So just to reassure people that there are no physics involved here.
Okay. Right.
5 microseconds per kilometer is more like it. Yes.
Okay.
Okay. I think we don't have more questions. Thank you very much, Dimitris. Very nice presentation. So we will move forward to the next speaker, who is Thomas Wolowitz from Thurn. And Tom is the original developer of the basic building blocks of the White Rabbit ecosystem and has been part of the core of the White Rabbit team ever since. Today, he will speak about the application of his timing technology in the context of the upgrade of the low-level RF system, which is extremely demanding timing, has extremely demanding timing requirements. So please, Thomas, the floor is yours.
Hello, can you hear me?
Yes, perfectly.
Yes.
Perfect. So good morning, good evening, good afternoon. My name's Tom. I represent here the controls, electronics, and mechatronics, as well as the RF radio frequency groups at CERN. And I would like to say a few words about the low-level RF system upgrade for the CERN Super Proton Synchrotron, where we extensively used the White Rabbit and MicroTCA.4. So, to provide you a bit of background, 5 years ago in 2016, CERN had decided to renovate the low-level RF controls, what drives the RF cavities in the SPS, from a very old analog system designed sometime in the 70s to a digital-based solution. And furthermore, we decided to benefit from White Rabbit for the entire clock and RF signal distribution in a digital form. This posed quite demanding requirements for the precision, like 1 degree at 200 megahertz, which corresponds mostly to more or less to 13 picoseconds, as well for the phase noise, the -130 dBc at 1 kilohertz offset at the cavity frequency. Back then, White Rabbit could not reach this figure, so we had to spawn several projects in order to achieve that, and I will tell you a bit more about these projects in the following slides. A quick overview of the low-level RF system. It's based around 2 micro TCA crates, micro TCA.4 equipped with the DESYS low-level RF backplane. One is called the cavity controller, which drives the 200 megahertz RF cavities. The other one is called the beam control, which coordinates all the cavities together. And furthermore, it calculates something what we call the RF train, the momentary RF cavity frequency that is then distributed over the White Rabbit streamers and White Rabbit network to all the nodes in the system. The clocking, that means the data acquisition clocks, 500 megahertz, and the local oscillator clock for the up and down converters is provided in these MTC.4 crates by the ERTM1514 modules. These are cards that sit in the special slots of the DESYS low-level RF backplane and provide ultra-low jitter clocks for the system. Furthermore, for interfacing with other subsystems in the accelerator, such as instrumentation, phasing with another machines, kickers, etc., we developed something we call White Rabbit RF VME. And 2 last developments that are supporting technologies, the low jitter version of the White Rabbit switch, and something we call LPDC, I'll tell you a bit later about, allow for improved precision and phase noise of White Rabbit in general. So the first design, the ERTM1415, is basically a very high quality White Rabbit receiver, providing 2 DDS synthesized clocks. We call them a local oscillator and ref that can be tuned between 10 and 300 megahertz with multiple outputs to the front panel and also the low-level RF backplane. Then there are 2 digital clocks, mainly for driving ADC syntax, with a selectable frequency, also multiple outputs. There are 2 White Rabbit uplinks available, standard timing I/O such as BPS and 10 megahertz. The board can be controlled over the USB port. Here there is a Python and C library provided for that, and also it can be used even without a micro TCA crate when powered from a bench power supply as an independent high precision White Rabbit receiver. Physically, it's a sandwich of 2 boards. There is a digital board with the FPGA Kintex 7 connected with a high-speed cable from Samtec with the analog board that contains all the oscillators, clock synthesis, and distribution. On the picture, it's a bit upside down, so the analog is up. The digital is the bottom one. So how did we achieve this -130 dBc phase noise figure as requested by the specification of the system? Well, this is well above the PLL bandwidth offered by standard White Rabbit, the offset of 1 kilohertz, whereas the PLL works at 200 hertz more or less, and also way below the phase noise floor provided by the FPGA transceiver. So we had to pick a local oscillator that is stable enough in free running mode at this frequency offset. We chose 100 megahertz OCXO from Axtal. This 100 megahertz needs to be further multiplied to deliver the master clocks for the DDS, 1 gigahertz, and for the clock distribution with sufficiently low jitter. So we took PLL with another discrete surface acoustic wave oscillator in its feedback loop, working natively directly at 1 gigahertz. So this way, we achieved the figure we promised. So the left figure shows the local oscillator output from the DDS, clearly -130 dBc. This is measured by an Agilent T5052. The digital clock outputs show a similar performance. There is, of course, a shift of a few decibels because of a frequency difference. The integrated jitter figures are way below 100 femtoseconds from 100 hertz and above the integrating range. Interesting curiosity at this level of jitter, even the mechanical vibrations start to matter. So the spurs you can see here actually come from the vibrations caused by the fans in the crate. The next serious development we had to undergo is the so-called White Rabbit 2RF VME card. It's a VME64X module the goal of it is essentially replacing all this coaxial cabling for the classical RF and trigger distribution with a single White Rabbit fiber. Timing-wise, it is equipped exactly with the same clocking and DDS system as the RTM boards, but it can furthermore produce two independent RF signals. That's because it contains IQ digital to analog converter followed by a mixer. The actual synthesis of the RF cavity signal is achieved through a so-called numerically controlled oscillator. And these RF outputs can be also used to produce all the sorts of timing patterns, timing pulses synchronous to RF through the trigger units. There are also a number of standard timing IOs such as the PPS and whatnot, and the board has a very simple to use API in C. So at CERN, we use it for driving systems that need the beam synchronous triggers or clocks, such as beam instrumentation, kickers, phasing with the proton synchrotron, which is the injector to the SPS, and so on. We aim to reuse this board to replace further analog cabling with White Rabbit. So how do we synthesize the actual RF? So the data stream produced by the beam controller, the micro-TCA crate, is received by the White Rabbit streamers, and it contains some high-level parameters that are specific to the SPS machine that get fed to the so-called RF-NCO core. The RF-NCO inside has a rather complex DSP chain that in the end produces the sine and the cosine of the momentary RF phase, which gets IQ demodulated, upsampled, and feeds the external digital to analog converter, followed by a mixer. This way we get our 200 megahertz cavity output, which has a performance phase noise-wise quite similar to what the RTM offers, minus 132 dBc at 200 megahertz. Last but not least, we had to greatly improve the White Rabbit precision in order to meet this 13 picoseconds goal, and also to improve the power cycle to power cycle phase reproducibility of the system. So standard White Rabbit offers roughly 100 picoseconds of precision, and most of this contribution comes actually from the FPGA transceiver, which at least in the Xilinx platform comes from two sources. So the phase aligner in the PHY and various clock dividers, mostly the high-speed serial clock to the parallel clock divider. We developed something we called LPDC, low phase drift capable, in order to tackle that problem. The detailed description of this is in the bibliography of the paper. I would just let you know this is supported on the Vertex 6 and Kintex 7 series FPGAs in the newest White Rabbit switch, the RTM, also the Spec 7 board from NICEF. More details in the paper. That was the technical part, well, White Rabbit part. I mentioned at the beginning of the presentation that this system is entirely based on micro-TCA.4. This was also the very first practical application of MTCA.4 in our accelerator sector. And it came as such with a few, let's say, childhood troubles. Probably the one that took us the most of the time was our collaborating institute requiring a signature of a non-disclosure agreement in order to obtain the very basic snippets of schematics of certain cards. That was blocking for us. We couldn't continue our work until the legal stuff has been sorted out. MTCA also suffered a bit from thermal design issues.
You have 2 minutes, Thomas.
Overheating, insufficient airflow, in particular the rear power modules and the RTM slots. We had a bunch of troubles with communicating with the power modules and the RTMs in the low-level RF backplane. We tackled bugs in the MCH firmware. Some configuration parameters did not work as expected. And one last remark, the configuration process is very complex, and sometimes by fiddling too much with the BIOS settings of the CPU in the MTCA crate that we had, check the, this is the exact platform, there is a risk of permanently damaging the CPU module. Luckily, thanks to very supportive hardware vendors, after some months of very fruitful collaborations, we managed to fix all these issues, and MTCA is now fully operational in the SPS. To summarize, this ambitious goal of driving a low-level RF system with White Rabbit spawned multiple developments, hardware, software, firmware, increased certain parameters of White Rabbit gear by an order of magnitude, if not more, enabling new areas of applications. For example, vastly improved phase noise. We proved that micro-TCA.4 works after a little of bug fixing. Now it's a suitable platform for us. As far as I know, it's one of the first, if not the world's first, fully digital low-level RF system that entirely relies on White Rabbit for synchronization, distribution of RF driving cavities. It has worked successfully for over 4 months with a physics beam in the operational machine at CERN. And all of this is available as open source software, hardware on the OHR. I would also like to thank the entire team. There was a lot of people involved. Thank you for your hard work and effort to make this happen.
Thank you,
Any
Thomas.
questions?
Very nice presentation and work. Time for questions. Check. I have one question regarding your last sentence. I mean, it's very nice to see the White Rabbit performance even increase with this for low-level RF. Are you now you have changed? You have done a test with micro-TCA.4. Are you planning to use this platform in the future after I'm focusing your last part of the presentation? You consider it stable enough?
I think there are some preliminary plans to renovate more machines with the same platform that we developed for the SPS, but no binding decisions have been taken yet.
Okay, thank you. I think there is one question from Ralph Steinhagen. Sorry if I didn't pronounce it properly. Kudos to the White Rabbit team. Ah, okay, sorry. It was just we can hear you have a congratulation message in the Q&A.
Thank you, Ralph.
So a quick question from myself as well. Tom, do you have an idea of whether you have reached the ultimate limits in terms of precision, accuracy, jitter, or do you still think that timing system based on White Rabbit can go lower as for jitter?
Difficult to say, but you can always put a better oscillator, reduce the PLL bandwidth. For White Rabbit, the limit is in the low frequency area. For the phase noise is the floor provided by the FPGA PHYs, but we are not limited to the transceivers integrated in the FPGAs. If somebody makes a proper ASIC or uses a discrete PHY or an external CDR, perhaps even smaller jitter figures can be achieved.
Thank you.
Thank you.
Thank you, Thomas. And so let's move to the next speaker.
Thank you very much.
Our
you.
next speaker is Pengxian Yu from SSRF in Shanghai. Pengxian is a control system engineer working on several projects related to the timing system of the Shine XFEL and the SXFEL user facility. Today, he will speak about the work he and his colleagues have been doing to develop a timing system for Shine based on White Rabbit. Pengxian, the floor is yours.
Can you see my slides?
Yes, and we can hear you as well.
Okay. Thank you very much for the introduction. Today, I will talk about what we have done to the prototype of White Rabbit-based beam synchronous timing system for Shine. This is the outline for my presentation. First, I will give you a brief of the overview about Shine project. Then I will focus on the architecture of Shine timing system and the prototype's development. Finally, I will give a conclusion about what we have done for the Shine timing system. Okay. Shine project is also called Shanghai High Repetition Rate X-ray Free Electron Laser and Extreme Light Facility, which is the first hard X-ray fair light source in China. The facility is built in a 3.1 kilometer long and 29 meter deep underground tunnel at Zhangjiang High Technology Park with 1.0030864 megahertz repetition rate. And this diagram shows the architecture of the Shine timing system. It will be composed of one master node about 80 White Rabbit switches and more than 600 slave nodes. The master node received the reference signal from the synchronization system. And there are three functions that have to be included in our Shine timing system, according to the priority from highest to lowest, which is the beam synchronous trigger signal distribution, random event trigger signal distribution, and the data exchange between the nodes. In order to achieve these required functions, there are several technical rules are proposed, such as the stand clock transmission, trigger distribution transmission, and RF signal distribution transmission. And I will then describe each of these technical rules in turn. About stand clock transmission, the stand White Rabbit network operates at 125 or 62.5 megahertz clock. If the repetition frequency of Shine is 1.0 megahertz, then the reference input signal can be divided to 10 megahertz as a reference signal. However, the repetition frequency of Shine timing system is 1.003086 megahertz. Therefore, we need to try other technical routes. For random trigger distribution, also called White Rabbit trigger distribution in White Rabbit based, White Rabbit trigger distribution is a generic framework for distributing triggers between nodes over the White Rabbit node network. However, there are several problems we have to consider if we want to use WTD system in Shine. First, the number of the trigger sources in the systems and the trigger repetition rate is limited by the network bandwidth and maximum acceptable latency requirements. And the jitter between the output trigger pulse and the input trigger pulse do not meet the requirement of Shine. And the repetition rate is too high. It means the 10 gigabit White Rabbit switches is also required. Unfortunately, there are no commercial products yet. By the way, according to what we heard from the White Rabbit workshop 2 weeks ago, there will be a release of the next generation White Rabbit switch with 10 gigabit for timing and data in 2024. WTD system was also used by SIR and Shanghai Soft X-ray Free Electron Laser User Facility. As we can see in the left diagram, which is the structure of the WTD system we used in Shanghai Soft X-ray Free Electron Laser User Facility. It contains one master node and 2 slave nodes. and the trigger comes into the master node distributed through a standard white rabbit network, and then fan out the trigger signal output through the slave node with a fixed delay. We have tested the performance of this timing system in the laboratory and also in operation. The jitter between the output slave node and the external reference signal is less than 120 picosecond. For RF signal distribution, which was also used by SIR and the ESRF, this technology could be adopted for our beam synchronous trigger signal distribution, but it needs further development. The slave node should output the low jitter pulse signal. Meanwhile, it is expected that the pulses can be configured for different field modes. Because the repetition frequency of Shine timing system is 1.003084 megahertz, we thought about the possibility of using this no standard frequency directly as the reference frequency. Therefore, we proposed a technology route of no standard clock transmission. Different from the standard clock transmission, now we consider if the 1.3 gigahertz RF reference signal can be divided to 1.003084 megahertz as the reference signal. Therefore, we have to figure out how to change. Can we change the white rabbit operating clock from the standard clock to non-standard clock? This was originally just an idea and eventually verified by the prototype development. Thus, we choose the technical routes, no standard clock transmission, and RF signal distribution transmission for the following prototype development. The prototype 1 we completed in cooperation with the Department of Engineering Physics, Tsinghua University, and we also carry out the prototype 2 development with the University of Science and Technology of China. First, begin with the hardware requirement for the prototype. As we can see in this figure, we provide two SFP interface. One is configured for white rabbit master or slave function, and another one is configured for standard Ethernet function. For the beam synchronous trigger signal distribution function, the level 1 WR switches is configured as a grandmaster mode, which receives the external reference and PPS signal. In the slave node, we also designed to provide 10 SMA connectors for the output signals, which include a machine clock with division or mask adjustable delay and pulse width. About the random event trigger signal distribution function, master node have to include 4 channels pulse input within 1 kHz. All the slave nodes need corresponding channels for output at the same time. Because of the consideration of particle need, an effective prototype mask mode need to be designed. Compared to a stand continue and equal space field mode, we decided to use a chain field approach, which means that the output pattern for the pulse from the slave nodes will be addable. But exact mask mode we have not yet finalized, is still under discussion. For the timeline of the Shine timing system project, we start in the second half of the 2018 with the technical route selection, prototype design review, and the potential vendor selected. And up to the first half of the 2021, we complete the integration, debug, and test of the latest version of the prototype and carry out a firmware and software development. About the prototype 1, in order to minimize the modification to the standard white rabbit equipment, the initial solution was to replace the voltage-controlled crystal oscillator of the switches and nodes, and shift the operating frequency to 7.7 megahertz. The system worked to use this customized VCXO, and less than 10 picosecond jitters was achieved. However, we find that the frequency factor which is 135 divided by 2, is not conducive to phase calculation and the pulse delay. Therefore, the operating frequency was changed to 64.197 megahertz, which is easy to generate 2 to the power of n divisions and thus obtain machine clock. Meanwhile, the frequency can be configured from the standard VCXO, not the customized ones. There is a clear proportional relationship between the stand second and the pseudo second. This is stand time format and this is no stand time format. There is a test platform for prototype 1. For the Bing's synchronous trigger signal distribution function, we test in laboratory, find the jitter between the output of slave node and the external reference signal is less than 10 picosecond. And for the random event trigger signal distribution, the jitter between the output of slave node and the external reference signal is less than 60 picosecond. The system architecture of the prototype 2 is shown in this diagram. Distincted from the previous mentioned RF signal distribution transmission. Consider that the final signal we need to obtain in Shine project is a low jitter pulse signal. In this prototype, we need to use the off-chip phase discriminator circuit to complete the measurement of the phase difference between the input RF signal and the clock signal output from the DDS, and output the pulse signal with the same frequency and the phase. Finally, through the fan-out and shaping circuit of the slave node, output
2 minutes
the
left.
pulse signal we need. And this is a test platform for the prototype 2. For the beam synchronous trigger signal distribution function, we also test in laboratory, find the jitter between the output of slave node and the external reference signal is less than 20 picosecond. And for the random event trigger signal distribution, the jitter is less than 35 picosecond. For the conclusion, 2 prototype system was development, both contain 3 functions, being synchronous trigger signal distribution, random event trigger signal distribution, and data exchange between the nodes. And the node standard clock transmission was proposed and verified. The prototype development has just been completed, and we will do further test and evaluation for the Shine project. Thank you for your attention.
Thank you, Pengxian. The floor is open for questions now. I have one question. So what is your timeline from now on to decide between these 2 ways of distributing RF, the non-standard frequency and the standard frequency with DDS? Is this a decision that you have already taken, or will you take it in the future? And if so, when?
We are now building a high repetition rate accelerator test facility now, and which will contain 1 or 2 cryo module with the same operating frequency. And we will use these 2 type prototype in this facility and to test the function.
Okay, thank you. Any other questions? If not, thank you, Pengxian, again. And let's move on to the next talk. We are changing gears now and to another domain where timing is critical, which is taking quick decisions inside FPGAs. Our next speaker is Stephen Roach. Steve is an undergraduate at the University of Pittsburgh, where he studies physics and math, and he's presenting on behalf of the Hong Group, whose research interests include using machine learning in real-time systems. Steve?
All right, thank you, Javier, for that introduction. Like he said, I'm Steve, and today I'll be discussing very low latency machine learning using boosted decision trees on FPGAs. So the tool that our group has developed is called THBR. This tool allows for the evaluation of boosted decision tree classifiers on FPGAs, providing very low latency for real-time evaluation. We've published a paper in the Journal of Instrumentation that anyone can take a look at. Our preprint is up on the archive. And we also have a website and a GitLab for anyone who's interested in learning a little bit more or maybe using our tool. So this talk is going to have 4 sections. I'm going to briefly discuss an introduction to boosted decision trees. I'll introduce our motivation for taking decision trees and putting them onto FPGAs. I'll discuss the optimizations that we make in order to do this efficiently and quickly. And then I'll give you an example problem and go over some more general results that we can come up with from this. So first, I'm going to quickly introduce boosted decision trees. This is a machine learning method that, amongst other things, separates classes. So for instance, signal versus background. And it does this by cutting on variables as you go down the tree. So in this example case, you have an event that's defined by 3 variables, X, Y, and Z. And you simply recurse down this decision tree until you end up in a category, which in this case would classify this event as signal. Oftentimes, decision trees will come in forests. So what will happen is many decision trees will be trained independently and given weights through a process known as boosting. So, and what happens is the event is given to all of these trees, each of which independently score the event. And the event is determined by the weighted average of these trees. So in this case, for 10 trees that are all assumed to have approximately the same weight, if 9 were to classify an event as signal and 1 as background, the event would be determined to be very signal-like and likely accepted as signal. So what is our motivation for taking this classifier and putting it on custom electronic systems like FPGAs? Our group does a lot of work at trigger systems at the Large Hadron Collider, such as ATLAS and CMS. What trigger systems do is they'll take the 40 million bunch crossing collisions per second at somewhere like ATLAS, and it'll reduce it in total to somewhere between 1 and 10,000 per second that will get saved offline and later evaluated. This is generally done with a 2-level trigger system. The first level will take the 40 megahertz input and will reduce it to about 100 kilohertz. And it does this using custom electronics and relatively simple algorithms that are on FPGAs and ASICs. This will pass about 100 kilohertz onto the high-level trigger, which is a CPU farm that often runs more complex algorithms. At the moment, machine learning algorithms are often performed on the high-level trigger, but our goal is to be able to implement machine learning algorithms such as boosted decision trees on the level 1 trigger. So how do we go about this? Our design philosophy is the boosted decision tree classifier is trained once in software, and this is done with an external machine learning package. What we do is we will take this trained forest and process it with THBR, which optimizes it and loads it onto the FPGA. Now, in real time, the FPGA will simply take in input events and it'll evaluate them with the boosted decision tree that now lives on the FPGA, and it'll output the score, whether that's a signal or background event, for instance. So our approach to do this had to be engineered a little bit. So in general, boosted decision trees are evaluated in the way that I showed a few slides ago, where you'll take the input and you'll recurse down the tree in order to find what bin the event lives in, and then just return that score. Unfortunately, FPGAs are generally not very good at things like this. And we will also wanted to take advantage of certain aspects like parallelization that are very good for FPGAs. So what we said is consider a tree like this that evaluates a 2-variable problem. What you can do is you can plot the bins that events would eventually fall into alongside their cuts. What we decided to do was if you extend those cuts throughout the entire grid space, what you're left with is what I have boxed in here, this nice rectangular separated grid space. And what the FPGA does is it essentially will find which bin the event lives in, and it'll just pick out that score. So we've turned this from a recursive problem into a binning problem. So on the FPGA, we have what's called a bin engine that's part of our firmware design. What this does is it localizes the data by bit shifting, which allows for a very fast way to find which bin each individual variable is in parallel. So in total, what happens is the event will enter the FPGA, and then for each tree, for each variable, it's binned in parallel. And then for each tree, the final bin is used with a lookup table to find the score associated with that tree. The scores are all summed up, and that provides the total output score. This design philosophy allows us to take advantage of things like parallelization that FPGAs provide the advantage for. There are some other optimizations that get made while we do the optimization. For instance, we have been able to merge trees by overlaying these grids that I showed. We've also been able to take advantage of things like using integer precision rather than floating point values in order to speed up evaluation. Some other optimizations that we've done include removing trees that have a particularly low boost weight and don't have much of an impact, and removing cuts that become redundant. So now that I've explained how this works, let's take a look at a sample problem to show it in action. So this is a problem that might be useful at a level 1 trigger system, where our goal here was to identify Higgs bosons that were produced in vector boson fusion. So what you'll see in the vector boson fusion production are these 2 jets that I've circled in red here. And when you compare those to just QCD multi-jet background, what you'll see is that you can take a look at some variables from them, and you'll come up with very different distributions. So what we did is we took these variables and we plugged them into a boosted decision tree and trained up a forest of 100 trees. What we were able to show here is that at the exact same level of background acceptance, this forest of boosted decision trees that we've trained was able to accept twice as many Higgs bosons as opposed to a benchmark trigger that simply put cuts on the variables rather than using something more complicated like a boosted decision tree. So what we've shown here is that for some problems, it could be advantageous to use machine learning methods such as BDTs at a level 1 trigger system. Now, the next step was, of course, to take this forest that we trained and put it onto an FPGA using FWX and see how it performed. So the results from the firmware performance are here. So what you can see is that the latency, the time it took to evaluate a single event took about 15 nanoseconds in this case. And the interval took about 1 clock cycle, and that's the time between you can start feeding new events into the FPGA. It also used very minimal amounts of resources on the board. All of them were less than 3%. And so for many use cases, this would be a very reasonable algorithm to load onto an FPGA. Now, this problem is one that we chose, and all problems will scale differently. So for instance, the latency will depend on things like the number of trees that were used, the depth the trees went, and the number of input variables that apply. That being said, for reasonable problems like we picked, we've been able to show that we can get very low latency, so less than 10 nanoseconds in some cases. And the latency is independent of the clock speed that you use because none of the operations are clocked. It's purely combinatorial logic. So this allows for a relatively easy integration into many systems. And the same trends will apply to the resource usage. It'll depend on things such as the number of trees, the depth of the tree, and the number of variables used. In addition, the integer precision that's used to represent the cuts and the output scores will have an effect. In this plot that I show here, you can see that there's a pretty wide variety in some of the points that seem like they should be next to each other. And that's actually due to the fact that different precisions are used.
2 minutes.
Thank you. So finally, just to wrap up what we've discussed, our group has developed this tool, FWX, that is very efficient at implementing boosted decision tree classifiers on FPGAs. We were able to do this by taking a novel approach to evaluating the decision trees and making some optimizations to allow for the best possible performance on the FPGAs. We believe that this innovation has the potential to allow for machine learning methods to be applied at FPGA-based level 1 trigger systems. So I demonstrated this by showing a problem that we considered the detection of Higgs bosons that were produced by vector boson fusion. This is very representative of one of those problems that a level 1 trigger system would have to attack. And it shows that in some cases, boosted decision trees may be better than existing cut-based methods that are used to solve these problems. We showed that we can perform better in the physics sense, and we can also do this with a good amount of efficiency, with very low latency and efficient resource usage on the board itself. So that's all I have. I'm glad to hear any questions if anyone has any.
Thank you, Steve, and thank you to all the speakers for respecting the time, which is, of course, very fitting for a timing track. So are there any questions? If not, I have a question about the algorithms. How specific are these machine learning derived algorithms to the problem at hand? I mean, can you make it generic enough that you don't have to reconfigure your FPGA if you're studying another type of Higgs production or something like this? I mean, how do you intend this to be put in production? Will it be running for the whole year with the same bit stream, or will you have to change from time to time?
So that's a very good question. In general, it depends on the problem. So for instance, the trigger developed is only really designed to identify things that were produced via vector boson fusion, and you would need something else if you wanted to find Higgs production via gluon-gluon fusion, for instance. In general, what we would like to, like I said, it would depend on the application for a lot of these things, but the physics really doesn't change. So barring some very large development, you would really not retrain the algorithm. What would ideally happen is you train the algorithm one time based on simulations and physics that you already know, and then load it up onto the FPGA, and during data taking, that same exact algorithm would keep running without you having to stop and retrain it at some point.
Mm-hmm. I see. Thanks. Any other questions? Okay. If not, thank you, Steve, again.
Thank you.
And our last speaker in the track is Stephen Coleman. Stephen is a research scientist at Radiasoft, where he is involved in several projects related to the modeling of high-intensity beams and laser plasma accelerators. Today, he will speak about a scheme for very fast control of laser focal position. Stephen.
Hello, everybody. Can you see my slides and hear me?
Yes, perfectly.
Great, thank you. All right, so today I'll talk about an integrated scheme for online correction of laser focal position. So just to give a little bit of motivation, since it's different than the other talks in the session here, high intensity lasers are a critical technology for present day and for future accelerators. And our interest in particular is for laser plasma accelerators with our collaborators at the Bella Center at LBL. A little diagram of a laser plasma accelerator shown here down at the bottom, where a laser impinges on actually two sets of two plasmas. One plasma is shaped plasma that acts as a lens, and another is a plasma in a discharge capillary that drives a wake field that accelerates electrons up to GeV scale in a centimeter long scale accelerator. So this is a very exciting and new technology. As you can imagine, laser alignment and control is very important for this application. So there are new technologies that permit us to make real-time assessments for quality assurance. Now, these machine learning and FPGAs aren't exactly new, but they're new for this purpose. And these 4 bullet points here are really the 4 steps in order that we need to take to make this happen. So we can take data from imaging sensors of the laser and use these as inputs to a neural network for some quality assurance. From there, once we have that in hand, we can use neural networks to then separately train them and produce corrective adjustments to control the laser using those imaging sensors. And then finally, we can put that training neural network or that corrective neural network on an FPGA, so we have a low latency inline control of this laser. And then it's possible to update it or upgrade this if we need to using the same hardware. So these 4 steps are the outline of our project, and we're really going to talk today about just step 1, which is where we are. So as I stated, the focal position and the different parameters of the laser are critical for these laser plasma accelerator schemes. You want to have an incident laser wavefront that is optimized for this purpose. And the focal position of that laser is sensitive to a lot of environmental and beamline factors that have very different timescales. So there are optical vibrations that might be high frequency, but you also might have temperature fluctuations in the lab that are low frequency. And so these, with frequencies of about a hertz for the high power laser pulses, you want to be able to correct for all of these things at various different frequencies. There are adaptive optics that one might use for this kind of purpose, but since we're talking about terawatt and petawatt lasers and adaptive optics, which might give some nonlinear responses, you open yourself up to potential damage if your adaptive optics drive your laser somewhere that it shouldn't be with a petawatt laser. So we want to have a fairly simple correction scheme, and we want to measure as closely as possible to the interaction point. Okay, so here's a cartoon of the Bella Center setup. So at the top here, you can see that there is a 1 second high power pulse, but there are also 1 millisecond secondary pulses that we can use for tuning and for correcting in between those 1 second high power pulses. There's a target chamber here, this high power focus point in the square box sort of to the right of center is where the plasma capillary would be. And so we have 3 things here, 2 sensors and 1 correction point. So on the right, this far field camera positioned here, we have a wavefront sensor, but this is downstream of the high power focus point. And so this can't be used in operation because the beam would be destroyed. It's destructive to go through the capillary. So we can't use that for tuning. We also have this in purple, this near field camera, which picks off before that high power focus point. So that camera could be used, wavefront sensor, excuse me, could be used in operation. And that thing itself could control, or output from that could control a beam expander, which is basically a telescope on a translation stage in the early part of the beam line. So the goal here is to tune that near field wavefront sensor to drive that beam expander. The two wavefront sensors that I mentioned, the one that's downstream, that it's in the perturbed beam line, is this Hasso wavefront sensor, which has a fine resolution and is a nice wavefront sensor that outputs a lot of secondary data as well as the image itself, but it has a relatively slow read frequency, which does not match the secondary pulses that we need to control the beam expander. So we're using that one sort of as a proxy for what the capillary sees. So this is the truth value, basically. And in the near field position, we have this Thorlabs camera, which is a little bit poorer resolution. Pixels are a little bit larger, but it does have a 1 kilohertz read frequency, which does match nicely with the secondary pulses that we're looking to measure. So we take a few steps to pre-process the data before trying to apply it to a neural network. We mask noisy or low information pixels, which are primarily around the edges of the peak of the wavefront. We fit the wavefront sensor data with Zernike polynomials, which are a set of basis functions that are used commonly with wavefront sensors. I've shown the first two orders of those here. So what we do is we take the wavefront sensor image, which is shown here in the bottom left, subtract out the higher order, or sorry, the lower order terms, and what we're left with is a map here that shows some of the finer grain details that are apparent in this image. That might help us to understand what's going on upstream of the beam, and to train that to control the telescope. So once we have this difference imaged here, we can add that to, or feed that into neural networks. We've tried a couple of different things here, and like I said, we're on step one of this process. First, we tried to feed this to a convolutional neural network, which is something that is commonly used for image classification and processing of images in neural networks. And so the convolutional neural network scans over the image looking for features and goes through several hidden layers. And what we're able to do is basically it's a expensive regression method. What we get in the output is a radius of curvature. So what we're doing here is using that Hasso wavefront sensor as our ground truth and trying to use the Thorlabs wavefront sensor to predict it. We explored architectures with two different convolutional layers and with and without dropout. And the plot here is one of our highest performing architectures where we still get a correlation between those two wavefront sensors that's good but not great, a correlation of 0.63. So we have also tried to apply this to a feed-forward neural network. So in this case, we take the image from the Thorlabs sensor and just treat it as a long vector where each pixel is a value, an element in that vector. And this allows us to also augment that data set by including some of the other scalar outputs that come out of the Thorlabs hardware. So Thorlabs actually does its own Zernike polynomial fit in their own hardware and outputs that along with the image, so we can feed that in as well. And this is still in development. We still need to do some data cleaning for these new variables, but in early tests, this is also showing us a better but still not great performance, where we get a correlation that's about 0.71. So better than what we're seeing with convolutional neural network, but probably not what we need for final performance. So once we have a neural net that satisfies our needs here, we plan to put this onto an FPGA to have inline to burn into a Cyclone V GT, which is a development board that is intended for OpenVINO, which is a nice open source package for synthesizing and simulating FPGA performance. And so since our neural net is constructed in TensorFlow and Keras, that feeds nicely into OpenVINO. So we should be able to just take that neural net directly, put it on the Cyclone board, and have our 1 millisecond response rate that we need for those continuous updating with those secondary pulses in preparation for our high power petawatt pulses. So to conclude, the three big takeaway points here are that high intensity lasers are critical for future accelerators, including these laser plasma accelerators driving GeV Wakefield electron beams. We're trying to use machine learning and FPGAs to control those lasers inline in real time, online, to control these high power lasers that operate at 1 Hertz. Thank you. I'll take questions.
Thank you. And thank you again for respecting the time. Any questions?
I have one question. The 1 millisecond latency that you showed, it's including this pre-processing that is needed of your camera?
Yes. So
if I understood properly. Yeah.
Yes. So the processing of the camera, and then to the FPGA, and then to control the beam expander, we hope to have, if not every secondary pulse, then some subset of these secondary pulses between the high power pulses. So we're not sure exactly what our latency is going to be on that FPGA once we have our final neural network. It could be, we're not sure how many clock cycles it's going to take to work it through the FPGA. But our goal is to get down to this 1 millisecond level.
Any other questions? If not, thank you to all the speakers and to all the attendees for a very interesting session. And I invite you all to join the poster session. You will find a link from the Huova interface, the Huova page for the conference. Thank you.